time to start, definitely. It's 1:45. Welcome to the session D326 about prototyping tools. My name is Niccolò Becattini. I'm assistant professor at Politecnico di Milano. I'm a mechanical engineer and I have the luck to chair this session, which is a nice one. Because all the presentation are somehow focusing on a very interesting topic, which is prototyping. And most of all, two of these papers received the reviewer's favorite award. So let me start with an overview of the papers that we will see during this session. The first one is entitled Proto-Booth towards an improved tool for capturing prototypes and the prototyping process. It will be presented by Lorenzo Giunta. His co-authors are Gopsill, Goudswaard, Snider, and Hicks. Lorenzo is a postdoc at the University of Bristol. His doctoral research focused on the design and development of spatial augmented reality systems to support collaborative design. This is the first paper receiving the reviewer's favorite. The second paper, it's entitled Proto-Arch, guidance tool for prototyping of mechanical system at the embodiment design phase. It is presented by Felipe Gutiérrez Morales. His co-authors are Osorio and Córdoba. Felipe is a research assistant at EAFIT, I hope I'm pronouncing this properly, University in Colombia. His research focuses on technical system development with CAD tools. The third paper is entitled Prototyping in Smart Product Design, Investigating Prototyping Tools to Support Communication of Interactive and Environmental Qualities. It is presented by Jing Wang. I hope that this pronunciation is good as well. Her co-authors are Ranscombe and Eisenbart. She's a PhD candidate from Swinburne University of Technology with a major in industrial design. The fourth paper, which also received the reviewer's favorite award, it's entitled The Interplay of Subjective Quality Evaluation, Prototyping Technology and the User's Technology Acceptance. It will be presented by Tina Buker. I hope that this pronunciation is good as well. And her co-authors are Endress, Miehling, and Barczak. Tina is a research associate at Friedrich Alexander University at Erlangen-Nuremberg, engineering design. The fifth paper, which is the last one, is exploring the benefits of remanufacture during product prototyping, a cost and time-based analysis. Ricardo Rial will present it. His co-authors are Snider and Hicks. He holds a PhD, he is a mechanical engineering student running his PhD now at the Design and Manufacturing Futures Lab at the University of Bristol. So this is pretty much everything from my side. I think that we shouldn't waste any further minutes so that we save a lot for the discussion. And I would kindly ask Felipe to start with the play of the recording. Thanks.
Hello and welcome to this presentation on Proto-Booth towards an improved tool for capturing prototypes and prototyping process. I'm Lorenzo Giunta and I'll be presenting this paper on behalf of the rest of my colleagues. Prototyping is an invaluable part of the design process. It allows participants to share knowledge between design team members and other stakeholders. However, due to the inherently unstructured nature of the process, prototyping is difficult to study and capture effectively. For this reason, various systems have been developed to aid in capturing prototyping and prototyping processes. However, shortcomings have been identified in many of these systems. This paper aims to analyze and improve upon some of these existing systems. This paper analyzed two prototyping capture systems, Proto-Booth and Archie. Proto-Booth was first conceived in 2017 as a tool to easily capture information. It was later improved in 2021 by adding additional cameras to better capture the full view of a prototype. The Archie system instead attempted a different approach. Rather than using multiple cameras, it had a single turntable with a single camera, allowing multiple views from prototype to be taken, but also attempted to improve on some of the original Proto-Booth systems by forcing the user to complete a survey prior to uploading their prototype, thereby capturing additional information rather than the simple image, which was often insufficient to understand what the prototype was supposed to convey. Some of the challenges identified in these two systems were the automation of the process for the data capture and post-processing, the ease of use of the system, the envelope size, allowing the prototype to be captured, the data presentation, and the capture of relevant data. In response to the challenges identified, Proto-Booth, an iteration on the pre-existing Proto-Booth system, was devised. Proto-Booth consists of two parts, an online software and a physical hardware. The online software part of Proto-Booth is a web-based interface and data collection tool which is hosted on a private virtual server. The software is run entirely from a browser on any device, be it either a phone, a tablet, or a PC. This allows any user to access Proto-Booth from anywhere in the world, from any kind of device, and utilize the onboard camera to interface with the Proto-Booth system and log pictures. Once logged into the system, the participant can create projects, add users, and upload prototypes to existing projects. When uploading a prototype, the system then prompts for 7 fields to capture. These are the names of the prototype, the project wherein this prototype is stored, other prototypes that have influenced the work being performed, the creator of the prototype, the description of the prototype, any rationales and insights that have been part of that prototype, as well as any of the files that wish to be uploaded, whether a CAD file, a picture, or anything else. The Proto-Booth hardware, instead, consists of a single board computer connected to a USB hub. This USB hub is connected to 3 cameras placed at 120 degrees from each other. The cameras are movable and are able to slide up and down, as well as translate across 2 different pivoting points. The single board computer then plugs into a monitor that can be interfaced with by means of a keyboard and mouse interface. Inside the Proto-Booth area, any prototype can be placed and easily captured. The hardware is designed to automatically log into the Proto-Booth software, allowing users to quickly upload their prototypes. A pilot study was devised to test the capabilities of the Proto-Booth system. This pilot study consisted of a hackathon termed the Idea Challenge. Participants in the challenge were from 4 separate universities across Europe. Participants were 4 female and 10 male for a total of 14. All participants were informed that their final scores in the hackathon would be calculated using Proto-Booth, but they were not provided any specifics on how the calculation would occur. Due to the COVID-19 pandemic, however, and the difficulties of international travel, participants all had to work from their own labs. As such, video conferencing was used where necessary, and participants were not able to make use of the Proto-Booth hardware. Only the software was tested. The results of the pilot study are encouraging. Participants were willing to fill out all the fields when registering their prototypes, and they made good use of uploading more than just photos. CAD models, videos, and technical drawings were included in the uploads of prototypes. However, feedback collected after the hackathon indicated that participants were not overly pleased with the usability of the platform, as well as some of the features and functionalities. Furthermore, Proto-Booth usage was highly incentivized by the nature of the Idea Challenge. And as such, it is unclear whether engagement with Proto-Booth would be comparable in a different kind of study, and perhaps additional research would be required in this area. The devices that we used to demonstrate the need of multiple clients showed that the ability to engage with phones and other devices was helpful to participants. Furthermore, the linking of prototypes to visualize the influences was a feature that allowed for more in-depth understanding of the design process. This ability to analyze the data automatically and directly allows for Protobooth to be more effective as a evaluation tool for design sessions. In conclusion, Protobooth is more easily integrated with the design process, thereby incentivizing its use when compared to prior systems. The ability to access the online software from any device has greatly improved Protobooth in comparison to many of the other predecessors. However, this does have implications for user interface and development, in particular where the need for supporting multiple types of browsers, multiple types of platforms, multiple types of devices is concerned. Future work should probably focus on the use of photogrammetry or machine learning to help simplify the process further, perhaps capturing any part of a prototype directly by scanning it and immediately logging and creating either a bill of materials or providing additional feedback on whatever is being photographed. Thank you very much. If you have any questions, please feel free to ask.
Good evening. My name is Felipe. I'm a master's student and research assistant at the Hicks University, and I'm going to present our article titled Proto-Arch Guidance Tool for Prototyping of Mechanical Systems at the Embodiment Design Phase. The presentation has the following structure. First, an introduction to the research problem. Then, I will present the Proto-Arch, how it's composed, and its application to a case study. Finally, the conclusions and future work. Product development is becoming more demanding due to the constant evolution of the market, creating smaller gaps for innovation and generating a significant impact on the end user, while being efficient in terms of time and resources. To aid in this process, prototypes take place as essential tools to help a design team to move from concept to reality. Research shows that the effectiveness of prototypes depends on the designer's experience, driven by intuition and how they apply design knowledge and manage resources and processes. However, this is not enough to eliminate uncertainties regarding the influential variables when securing a prototype. This is where the proposal of methods and tools towards the prototyping activities are important. In research, there is evidence of tools and guidance to support prototyping activities, such as Likert scales for defining a prototyping strategy and more refined tools like the Prototype for X, the Prototyping Canvas, and the Prototyping Planner. Among others, it is agreed that prototyping is an activity that should be considered throughout the product development process, and a prototyping tool should be oriented towards the product design phases. These tools need to avoid open-ended questions, which is something recurrent in the mentioned studies, since they link to the user's considerations, the definitions of key variables to establish what and how to prototype. The construction of a Proto-Arch was based on two considerations. First, the product development phases, which we define as planning and task clarification, conceptual design, embodiment design, detailed design, manufacture, testing, and delivery, with the respective inputs and outputs as shown. The second consideration are the roles and purposes of prototypes, which help to answer critical questions towards a successful design. In this aspect, we reviewed what has been proposed in the literature and chose the work presented by Petrakis, with a list of 30 prototyping roles and purposes in the classes of exploration and requirement elicitation, learning, project planning, communication, design refinement, and system integration. With these items, the connection between product development phases and the purposes of prototypes was made. The prototyping roles and purposes were classified according to each product development phase, being the embodiment design phase the one with the highest number of applicable purposes for the fulfillment of its objective, from which the development of the Proto-Arch was derived. It's worth mentioning that the presented version of the Proto-Arch is the result of an early testing phase carried out with a group of 4 master students on how to use the tool and how the information is presented within its blocks. The case study focuses on presenting how the Proto-Arch works in the design problem for the electrification of an outboard engine, being the prototyping effort the splice interface between the engine and the gearbox. The tool structure has similarities to previous proposed work in the field, such as the prototyping canvas and the prototyping plan. The one-page sheet format is used following the recommendations mentioned in the literature of being simple and having a general scope of critical information about the prototyping effort. The Proto-Arch presents 5 main blocks as follows, that must be filled in sequentially. Block 1 first inquiries the user about the functional block. According to the design problem and the possible concept solutions, the user identifies the functional blocks referring to component or group of components within the prototyping intent. The splice interface has three main components, which are the lower frame, turrets, and upper frame, and for each one, all the functions they must execute are outlined. From the presented levels of integration of single function with actuator, subsystem with actuator, and full system, the user chooses the subsystem option. Therefore, multiple to-be prototype functions are marked 11 out of 14, along with their application principle within the options of conceptual visualization, geometric, functional, and technical. 5 functions have a geometric application and the remaining 6 a functional application. In Block 2, the available resources are defined with respect to budget, team members, dedication time, and time to deliver. The 11 to-be prototype functions are defined as specifications so they can be measurable and establish the level of execution for the final product and the prototype. Only specification number 2 has the same level of execution for both items. Block 3 presents a series of heuristics regarding parallel and iterative prototyping, considering the previous inputs of the user. As found in literature, Hicks scale legend is used and suggests for the prototyping activity to prototype one concept and one iteration. Block 4 presents a series of heuristics regarding virtual or physical prototyping, also considering the previous inputs, like the prototype functions and the specification for the prototype level, and proposes to create a virtual prototype. Finally, Block 5 introduces the spectrum of virtual and physical prototypes, each accompanied by an auxiliary table that indicates, according to the integration level, which techniques are recommended to be used and their priority depending on the application principle. Having a virtual prototype as a suggested dimension for creating a prototype, the user inputs all the to-be prototype functions and selects the applicable execution for each one, within the categories of 3D geometry and simulation. At last, a yes-no question is presented about the next stage for testing the prototype, which is marked with a yes. Conclusions and future work. The embodiment design phase presents the highest number of applicable purposes to fulfill its objective, and thus it is expected to present a high dedicated effort towards generating prototypes compared to the other design phases. The Proto-Arch is a tool to guide prototyping activities in the embodiment design phase of the product development process that establishes a throughout strategy for the execution of prototypes. The tool has closed-ended questions and guidelines on how the user should fill out its 5 blocks, establishing the prototype execution. Its use is from one specific moment in the design phase. Therefore, if the information is added, the tool should be run through again. For planned future work, the Proto-Arch must be tested with larger sample to have a better perspective about its usefulness, and define a testing protocol or guideline according to the prototype intent. This work is supported by the Alliance Energética 2030, which is a research program from the Colombia Científica initiative funded by the World Bank. These are our references. Thank you for your attention.
Hello everyone, this is Jing Wang from Sweden University of Technology. My project is Prototyping in Smart Product Design, investigating prototyping tools to support communication of interactive and environmental qualities. And there are 5 parts in this presentation. The increasing availability of smart products creates a more pronounced need for designers to prototype and communicate interactive and environmental qualities of product during their design process. Which elements of user journey, storyboard, and wireframe contribute to communicating these qualities, and how they might integrate with sketching. So we need to know the key elements of the user journey, storyboard, wireframe, and hand sketches. For instance, in user journey, there are 5 key elements. They are persona, timeline, emotion, touch points, and channels. And there are also 4 categories of sketch purpose: idea sketch, study sketch, usability sketch, memory sketch. There are 3 research questions in this project. In our first research question, we really just want to understand the extent of the tools are used by designers who are engaged by smart product design. And then we want to know which elements of the above tools are most important to communicate interactive and environmental qualities. And the follow-up question, here we know that hand sketch is important, so we will see how these tools might connect with sketching. A survey is used to learn from the participants' experiences and further understanding their prototyping practices for our study. And this survey is divided into 2 parts. And we have 50 participants, 38 with smart product experience and 12 without smart product experience. So here is the data. There are a number of interesting findings, but in the interesting keeping brief. This is the main findings. So this is the results are visualized in figure 1, and the data is used to answer research question 1. Figure 1 presents frequency in terms of 4 categories. They are don't use, frequently used, infrequently used, don't know. And the bar chart then shows the percentage of represents, indicating categories for the 3 tools and between the SPD and TBD groups. So in the SPD group, the wireframe is most frequently used tool, while storyboard is used most infrequently. Next, the data in figure 3 is the average for each element. The first element ranking counts as 5 points, and the fifth counts as 1 point. For instance, in user journey, the element most effectively used to communicate the interactive qualities of the product in SPD group is persona, which is also the same within the environment. There is only one difference in the ranking of elements in interactive and environment. In interactivity, the touch point is above the emotion, whereas the opposite in the environment. So there are 2 combination support in the survey. The combination support 1 is a combination of sketching elements and 2 elements. The combination support 2 is a combination of sketching purpose and 2 elements. And the results are listed in table 6 to table 8. And the ideal combination would be low-fidelity sketches that incorporate some user identification and illustrate timeline. The data indicates the use of annotation to assist in this rather than duplicating elements visually in a high level of fidelity. Temporal or contextual elements could be illustrated visually, but using the approach of wireframes to create an overall structure of interaction. So in summary, we contend the above combination of elements would support a more holistic communication of tangible and intangible aspects of smart products. So these findings provide a clear picture of the more important elements of existing tools in the practice of smart product design. And findings of this paper set the foundations to create and test such combined and hybrid prototyping approaches. So the further research to test their efficacy in communication are qualities of smart products to range of stakeholders. That's all. Thanks for your listening.
Hey guys, my name is Tina Buker and I'm from the chair of engineering design at Friedrich-Alexander-Universität Erlangen-Nürnberg. My research is all about user-centered design and effective engineering. And within this research, I often have to deal with the subjective quality of a product, how it can be evaluated and how it can be improved. As subjective quality of a product is a fundamental aspect of today's presentation, I want to make sure that we share a common understanding about it. So before we begin, let's just quickly talk about what it is, how to measure it, and what we should evaluate. So when we talk about subjective product quality, we talk about satisfaction, joy, pleasure, beauty, attachment, motivation, and values which the product represents. These are all different dimensions of subjective quality, and we can already measure them with tools from literature. For example, we can use the attractive, the MIQ questionnaire, or impressions profiling, which is part of a KD and measures the user's attitudes and values towards a product. The moment we know what we would like to measure, we also have to decide what to evaluate, and this strongly correlates with the when. We all know that design changes usually become more expensive and difficult as the design process continues. Thus, we shouldn't wait until the end of the design process. We need to do this much earlier. And this means, of course, that we have to work with, let's formulate it as approximations of reality. And this means that we need some kind of prototype. For subjective product quality evaluation, this prototype does not necessarily have to be fully functional, but it at least needs to represent the form and shape of a product adequately. And there are different prototypes that we can use for this purpose, like 2D images, 3D printed prototypes, or virtual prototypes presented in virtual reality or augmented reality, and of course many more. The challenge is that we don't know what kind of representation we should use to enhance a realistic and reliable evaluation of subjective quality. We wanted to contribute to this question and therefore examine the interplay of subjective quality evaluation, prototyping technologies, and the user's technology acceptance. What we asked ourselves in particular was, first, whether different forms of product representation influence subjective quality evaluation of prototypes, and which of them provide the most realistic image of a product's subjective quality. And second, whether a person's technology acceptance influences the subjective quality evaluation of a prototype. To answer these research questions, we conducted an empirical study that included lab sessions with 24 persons. Thereby, one participant assessed 3 product demonstrators, which you see here, a vase, a water sprayer, and an ergonomic knife. All demonstrators were presented as images, 3D printed, and in VR and AR. Let's quickly talk about the procedure of the study. During lab sessions, we first collected general demographic data from the participants and their general technology acceptance independent of any prototyping technology. Afterwards, the participants were shown all 3 product demonstrators presented within the different technologies. And the participants were asked to assess the subjective quality of the given prototypes with the impressions profiling from a KD right after observation. So for example, the participants saw the vase as an image and assessed it right away, then the water sprayer, then the ergonomic knife. After that, we gave the participants a questionnaire to assess the technology acceptance. Then the same process began with the next technology. So it was the same with the 3D printed prototypes and the representation in virtual reality, and finally the representation in augmented reality. To have a comparison with reality, the participants had to assess the physical products as well. The lab sessions ended with a ranking of the used technologies from 1 to 4. As we do not have much time left, I am highlighting the main findings of the study. For a more detailed explanation, please feel free to read the paper or get in touch afterwards. So anyway, to answer research question 1, we conducted paired t-tests. And for each product, each impression, and each technology, we compared the evaluation of the prototype with the evaluation of the physical product. We then had a total of 60 tests, whereas 24 of them showed significant deviations. The best representation was with images, as they had deviations in only 2 out of 15 pairings. And the worst representation was with the AR representation. They had deviations in 11 out of 15 pairings. To answer research question 2, we conducted a correlation analysis where we examined the relation of the general technology acceptance as well as the technology-specific acceptance with the deviation of the evaluation between prototypes and real products. Hereby, we found 4 significant correlations. So looking at the person, we found out that people who often imagine complex issues visually, so for example, thinking in images and shapes, are able to evaluate 3D printed prototypes very closely to the real product than people who don't. Looking at the technology-specific acceptance, we've seen that participants who perceived pleasure and had a lot of fun using the VR application were not able to evaluate the VR representation closely to the real product. We assume that the participants were distracted from the actual task of evaluating the product demonstrators in those cases. Furthermore, we found out that participants who perceived the use of the AR application to be difficult also evaluated the AR representation less closely to the real product than those participants who found it easy to use. We think that difficulties in the usage of the tablet, which they used for evaluation, may have distracted the participants from the task, which maybe have led to a distorted presentation of the product demonstrators. Last but not least, we found correlations with the participants' experience. The more experienced the participants were, the closer was the evaluation of the prototype to the evaluation of the real product. We explained this with the assumption that experience may reduce usage errors and avoid distractions. Concluding, we have seen that different forms of product representation influence the subjective quality evaluation, and that the personal technology acceptance of a person has also a small influence. For practitioners who want to measure subjective product quality with impressions profiling, we recommend to use images. They provide the most realistic results while, and that's actually pretty nice, being cost and time efficient. If you have any questions left, please feel free to join the discussion now or get in touch afterwards. Thank you for your attention. Bye.
Hello, I'm Ricardo Real from the Design and Manufacturing Futures Lab at the University of Bristol, and this presentation is on a paper titled Exploring the Benefits of Remanufacture During Product Prototyping. To begin, we'll show an example of a remanufactured part. On the left is a gear from a milling machine that has some damaged teeth, and on the right, this gear has been remanufactured using additive and subtractive processes to return it to a like-new functional state. In industry, this process is being increasingly used to repair parts instead of disposing and manufacturing new stock. Examples can range in scale from wind turbines to smaller automotive parts. A study into the life cycle of remanufactured automotive parts by the VDI Zentrum Ressourceneffizienz found a high percentage of savings across components in terms of energy use and resource use. In new product development, it's common for multiple iterations of a design to be produced before reaching a solution that satisfies a set of product requirements or an objective. So could a remanufacturing process be used to reduce the iteration time between versions of a prototype, and of course also reduce the resource use and cost of development? To explore the potential savings of a remanufacturing process in product prototyping, a three-step study was outlined to investigate remanufacture in the prototyping context. This included building and characterizing a dataset of prototypes with multiple versions of the same part, then simulating a remanufacturing process to go from version 1 of the part to version 2, and finally analyzing the time and cost of a remanufactured part against simply making version 2 as a new instance. To characterize the change between versions of a prototype, a dataset of 40 models was compiled with distinct changes between versions 1 and 2 of a prototype. Models for the dataset were found by using search terms V1 and V2 on the model sharing website Thingiverse. The difference between versions was measured quantitatively, for example, to look at volumetric differences, but also qualitatively to understand the rationale behind a design change and help identify different types of change for more detailed analysis. Following this, 3 approaches for prototype remanufacture were identified to allow remanufacture from versions 1 to version 2. These are Boolean, sequential, and multi-orientated, and further definitions for these can be found in the paper. In the second step, suitable models were selected from the dataset to investigate each of these approaches, and further, we used a cost model to analyze the savings presented by each case, looking at time and cost for remanufacture against making version 2 as a new instance. The cost model breaks down the remanufacturing process into 3 stages: pre-processing, where the toolpaths to remanufacture are generated; execution, being the machine setup and program runtime; and post-processing. This allowed for a more comprehensive analysis of each stage and its contribution to overall time and cost. To simulate the process, the values from the figure on the right were used for calculation. These values were based on experimental times for going through each of the stages. Looking at the results, we find that reductions in time are shown in cases A and cases C, although time is not saved in case B, as the model is fairly small and fast to fabricate. Where pre-processing times are high, the size of the model can have a significant impact on time savings. Looking at cost, it's evident that reductions are achieved in each of the remanufactured cases. From the breakdown of remanufacturing time on the right, it's clear that pre-processing, or the time to generate machine code, is the largest contributor to overall time across all cases. For energy costs, remanufacture is shown to achieve a reduction above 90% in each case. Whilst the values for energy used in this study are relatively low, if using processes with higher power requirements, then energy could be a greater contributor to the overall cost. A significant reduction is also seen in the material use, with over 80% savings observed in each of the 3 cases. As the scale of the models was seen to have an effect on the feasibility to remanufacture, the study was repeated at small, medium, and large scale relative to the build volume of a desktop 3D printer. We find that as the scale of the part increases, savings also generally increase, and this is due to pre-processing time factoring for less of the overall time to remanufacture. To conclude, pre-processing time is seen to be a big factor in the overall time to remanufacture. Reducing the time to pre-process could make remanufacturing more applicable to broader applications with varying scales. However, the cost savings from remanufacture could outweigh the increase in time for such cases, for example, if using high-cost or rare materials. To remanufacture currently requires some technical know-how in pre-processing of models, and also to set up the parts on a machine and run the program. If this could be streamlined, then remanufacturing processes could be more widely applicable. From this, future work could look at developing tools that streamline the remanufacturing process, particularly in the pre-processing stage. And finally, if such a tool were available, how might it affect the design outputs? For instance, how would reduced iteration time affect the development process? And also, how would it affect design outputs? Could using remanufacture in the prototyping stage lead to products that are better designed for repair and reuse in the future?
Okay. Thank you all for your presentations, actually for your recordings. Well, I think that we have plenty of questions in the chat, so I prepared some of them, but in the end, it's much more interesting to ask the audience to jump in the discussion and ask questions themselves. As long as part of the questions are from those who already asked the opportunity to share mic, maybe Felipe, who is the moderator, but it's also an active member of this meeting, he can ask his question to Lorenzo directly.
Yeah, thank you very much, Niccolò. So, Lorenzo, thank you very much for your interesting presentation. Basically, my question is regarding the Proto-Boot, because I was one of the participants in that study, but at the time it was not clear, is the at least not to me, is it Proto-Boot intention to be used as a tool for facilitating the prototyping process, or is it more like for archiving and backtracking what we have done so that we can basically evaluate our prototyping process?
Well, I would argue the two are not mutually exclusive. When Proto-Boot was initially designed, and the original idea behind Proto-Boot, the idea was to develop a tool that would allow to capture the prototyping process for researchers to kind of evaluate and gain insights into it. But this doesn't preclude the participants who've used it from querying it for more information. Now, in the context of the hackathon challenge, that's not super interesting, because once the hackathon challenge was complete, there was no real interest by many of the participants to go back and review their products. But you could imagine in, say, a long-term implementation, for example, in an industry or within a design consultancy, that having that ability to review the design process, checking against stage gates, for example, might provide helpful insights into the processes that are being performed, and not just act as something to be able to check what happened 3 weeks ago. Hopefully that answers your question.
Yeah, thank you very much.
So the second question is from Charlie Ranscombe. He is not within the ones allowed to share the mic, so I'm going to repeat his question. Charlie is interested in the willingness of designers to capture information with Proto-Boot. That is, do they see it as a chore? Were any capabilities tools viewed more or less easy to use?
So that was one of the things we were trying to improve Proto-Boot over previous iterations, and in particular the Archie system. It was something that Archie had already tried to address by forcing participants to fill out a survey prior to being able to submit their prototype. The reality is, yes, it's seen as a bit of a chore, in particular because participants don't immediately have a tangible feeling of progress from completing things into Proto-Boot. However, we focused a lot on trying to minimize the impact of this. By having everything web-based, it allows you to load up the entire interface on your phone, meaning that you can use the physical Proto-Boot hardware, which allows you to take more pictures and has everything logged in. But if you do only load the software element on your phone, you can have a handheld device that can take a recording, can allow you to capture things more easily, so to minimize that chore element of it as much as possible.
So let's move ahead with the question by Chris Cox, still for Lorenzo. What were the features of Proto-Boot that participants were less keen on, and how would you mitigate against these?
I think this ties in nicely with the previous question. I would say, yeah, the submission process, in particular filling out the forms that are required, things like what was the intent behind the prototype, could you link it to pre-existing prototypes, who developed this prototype. I would say if parts of these can be automated by having a bit more intelligence in the system, so automatically, if you link to a previous prototype, automatically adding the previous users who created the previous prototype to the new prototype. And I think, yeah, simplifying the submission process, and perhaps trying to look into some gamification elements. Perhaps it would be helpful if the participants feel that they're making progress and not just filling out text boxes like a checkbox exercise. But it's one step at a time.
Okay, Then one question from Camilla Antansen. Are there any direct value to the user of Pro2 booth apart from winning a challenge? For instance, are they presented with data about their own prototyping process or similar?
So I think, yeah, this question is similar to the one asked by Philip. And yeah, I think that the same answer pretty much stands. There is value for them, but within the context of a hackathon challenge, it wasn't really super valuable for participants. We did offer them the opportunity to look at the data and go back, but I think people who were interested in it were interested in the data from a research perspective, not from a how well did we design our prototype perspective. But yeah, I can imagine a larger research group or from a design company would have interest in seeing how and why and where the improvements we're making are being reflected in the design process.
Okay, last question to you, Lorenzo. It's coming from Tina. Maybe Tina, you would like to ask it yourself.
Yeah, sure. First, thank you for the nice presentation. I was wondering if I understood it correctly. You talked about the evaluation and that only a part of the participants used the hardware and the other part used the software. So how did you compare those findings? Are they even comparable? And what exactly did you measure during this evaluation and how did you measure it?
So none of the participants used the hardware setup precisely to allow for a more comparable setup. So we were only looking at the software elements. After all, the hardware side is a tool to facilitate the capture into the software side of things. We were mostly looking at how much data would be collected. So if participants were not filling out the forms, we could then infer that it was too troublesome for them to do that. Luckily, we found that all participants were filling out the forms consistently. We also provided them with a feedback form at the end of the design challenge to ask them on usability feedback. We provided them with a number of Likert scales saying how much of a chore was this, how fun was it to use, and a couple of other questions. Which allowed us to kind of collect feedback on general feelings of using the Proto-booth setup. Yeah, I would say that was generally what we were trying to see, both from a qualitative perspective of how well did people interact with it, how chore-like was the experience, as well as how complete a data set could we create using the Proto-booth setup, and what kind of data was being reliably captured through it. So intent, users who were designing the prototype, and creating a kind of a map that allowed us to link all of these things together. So hopefully that's answered your question.
Yes, thank you.
Please.
Okay, thank you, Lorenzo. We will probably come back to you later on. Let's move to questions for Felipe. The first one is coming from Philip.
Okay, hello, Felipe. I have one question regarding your Proto-Arch template. I see it's kind of similar to existing template from Camilla, and I see that you cited it, her in her work. I'm asking how long does it take to fill out this template? Because my experience with Camilla's template is that my students usually lose interest in filling all the blocks, and her template is a little bit smaller than yours. So what is your experience? How long does it take? And are designers willing to fill all the blocks in your template?
Okay, that's one of the most difficult parts when creating this type of tools. As you mentioned, with the similarities with the Camilla's work, I did 5 or 6 iterations of the Proto-Arch, and the mean time of use was about 10 to 15 minutes, depending on the complexity of the concept. And for example, with the case study that I presented with the engine, that it has 3 main components and a lot of functions, the designer took about almost 20 minutes, and it's really, they see it as was one of the questions that Lorenzo was asked, and it's something that maybe needs to be acknowledged in these tools and needs to be assessed and how to improve how the tool is used.
Okay, and can this tool, for example, be digitalized so that we can speed up the entry process? Because, for example, during the Proto-Boot idea challenge, we had like built 10 prototypes in a day. And if we lose 20 minutes to fill out the template, that's a lot of man-hour in a single day.
Yes, it's correct. Actually, I'm working in, this is like the bare bones version of the tool, because my intention is to build like a combined methodology of how to prototype and how to test the prototype. So I'm creating like a flow chart of these considerations of this tool, of how to prototype and how to test it. And in the meantime, it's just like a format you have to fill in with by hand, but it could be like a program in the future. So
okay.
Some sort of software.
Okay, thank you very much.
And then let's move to Charlie's question for Felipe. He says that it's a great idea to help designers and engineers prototype more intentionally. He's suggesting that some potential connections with quality function deployment. So actually, this is not really a question, but let's say, have you ever thought about potential connections with QFD for your tool?
I don't know. Regarding to QFD, I think I know it as a house of quality, right? And
yes.
Okay, so we thought about it to include it in the Proto-Arch, but as Felipe suggested, we added in the Proto-Arch structure, it will be too large for the user, but maybe I haven't considered yet for the methodology I'm working on to build this flowchart as an input for the functional block. It may be a viable option to include it.
Okay, so maybe now, before we move to the next presenter, I can try to ask you something. Since you thought these two to be focusing on embodiment design stage, if we think about the integration with QFD, House of Quality, I think that moves the application of that tool to the earliest stage of the design process. Obviously, you can use the House of Quality and QFD whenever you want, but typically QFD is meant to be used during the first phases of any design process. So what would you think it would be needed for your tool to address something that takes place during the earliest stage of the design process, which are the ones where the decisions are somehow less constrained, since if we move to the embodiment stage, some decisions are already well constrained by the previous ones, the ones you made during the previous stages.
Okay, as you mentioned, I only focused on the embodiment design phase, as it had the most quantity of purposes and roles for prototypes. So you expect that in this phase you are going to build a lot of prototypes. So you are going to consider, I'm considering that you already know everything about these previous stages of the design phase. You already passed throughout the conceptual design phase, and you already have these inputs about the design you are going to do. So I'm hoping that the designer is acknowledge this information before entering the Proto-Arch. So I'm going back to the question Charlie asked about integrating the QFD. Maybe I will need to integrate some type of other questions or blocks regarding the conceptual design phase.
Okay. So I would like to go ahead with a question for the third presenter, which is Jing. Maybe Jing, you can share your screen and open up your mic. Not the screen, sorry, the camera. We can see you at the moment. Now we see you and hear you. So the question comes from Lorenzo. Would you like to ask the question yourself, Lorenzo?
Of course. So yeah, I was asking on how you settled on the selection of 3 options, the storyboarding, the user journey, and wireframe. If this was from the designers you interviewed, because these were the strategies they were using, or they came from somewhere else, and do you think that a more descriptive approach to your process might have helped capture a more wide spectrum of tools and methodologies, or was the choice of these 3 things very specific, very deliberate to evaluate them and only them?
Okay, thank you for your question. So I did a survey before this research. So in the previous survey focused on the frequency of prototyping tools and satisfaction with their concerning prototyping tools used for communicating concepts with members from disciplines. And we had 2 groups. One is Smart Product Design Group, and another is Traditional Product Design Group. And we found that the Smart Product Design Group used these 3 tools more frequently than the TBD group. And we do a cluster analysis, also find these tools are in the same group. So these tools are low satisfaction but high frequency. And we want to improve this, find the similarities from these 3 tools and improve this. And the next is about the, because we want general answers from the participants, so we choose use a survey that I can get more responses. So that's all. I hope that answers your question.
Yes, thank you very much.
Thank you.
So maybe if there are no other questions coming from the chat for Jing, I can try to ask some questions from my side. So can you elaborate a little bit on what you presented for research question number 3? Since we got that that's about the combination of different elements from the tools, but I think that the audience would like to learn a little bit more about what you expect to combine from the tools you explored.
So the combination is based on 2 parts. One is from the sketch, and another is from the key elements from these 3 tools. And from these 3 tools, the key elements are related to the user and the context elements. So because these key elements are considered most important to communicate interactive and environmental qualities. That's my answer.
Okay. Is there anything that you did not expect out of the results you obtained from the exploration you did with these 50 participants? Did you expect exactly what you observed, or is there something which was not so expected, so in a way surprising?
Sorry, can you repeat your question?
So what I was trying to say is you got some results out of these 50 participants using these tools for smart product design or traditional product design. Did you exactly expect what you get as results, or was there anything surprising? So something that you did not expect at all.
So this is this survey is the first step. Then I get more responses, and then I want to find a different stakeholder designers, and I'm doing this research now, and I find that there are some similarities and also some differences from the different stakeholder designers, like different from the industrial design with UX, UI designers.
Okay, thank you, Jing. If there are no other questions for you, maybe we can come back to you later on. We can move to questions for Tina. And I see that still the first question comes from Felipe.
Yes. First of all, Tina, thank you very much for a wonderful presentation. Very interesting topic. My question is regarding VR and AR, augmented reality. So very similar technologies, and in this representation of prototypes, what is the main difference? Were they different? Were they perceived different from the participant? Is one technology better than the other? Do you have some conclusions on that?
Yeah, thanks, Philip, for the question. What we tried to do, and while choosing all those different prototyping technologies, we always try to just be kind of make a clean setup, to be like no high sophisticated prototype in comparison to another one. So the AR and the VR representation was kind of a clean setup, so both of them. But of course, there were differences in the setup. So in the VR, we just had a room, and there was a table, and the products were on this table, and the participants were able to just walk around it, but not that huge. So very clean setup. And within the AR, we used just an iPad, and then they had to do everything on their own. And we had a table in a physical room where they had to look at this. So I guess there are, of course, differences in the setup, of course, as they are different technologies. But we use the same CAD models, so this would be the same. But they, of course, were experienced differently. So as you've seen in the presentation, we've seen some. From the system side, we've seen some significant influences of the experience with AR, and I guess it was kind of the more challenging for the participants to use the AR application. So when you think about it, you might think that VR might be more complex, but within the VR setup, it was like the participants were there, and they got all the stuff on them, and then they were just looking around. And within the AR, they just had to do everything on their own. And so this might have a stronger impact on their whole experience and accepting this. So when the question with if one is better than the other, so when we asked them to rank the different prototyping technologies in the end, and VR and AR were kind of ranked the same, so nothing better than the other. And also within the paired t-tests, they were also kind of the same, but not that good. So I guess there were so many distracting elements within the whole experience and in the setup. Yeah.
Okay, interesting. Thank you very much.
Thank you. And next question is from Lorenzo.
Yeah, you've answered part of it actually, so I'll change that part. My first part of the question was about potential learning effects, because you mentioned that participants would go through one technology, then another, experiencing the same prototypes. Do you think that having done this, that this might have played a role in how people experienced the various technologies?
Yeah, so you're absolutely right. Learning effects may have a strong influence here, but we actually try to get over them. So not every participant had the same order. So we changed the order of the products we showed them, and we also changed the order of the technologies. So so each participant had a different order of products and technologies. The only thing that was the same for all of them, that the physical products, so the reality evaluation was at the end. So, but it might also be that the first might have the most impact on them, and then the others. So, but I guess that the study design as it is now does not allow to really answer whether we have learning effects or not. So I guess we cannot make a valid assumption here, but we try to avoid it the best we could. But yeah, it's a huge problem in making such such studies.
Good point, Lorenzo.
If I can ask you to take part of my question as well, sorry. I was just wondering, because you mentioned that you used a tablet, have you looked at other AR technologies? Because we ran some experiments with comparisons of AR technologies and found that people don't tend to like holding a tablet all the time. It's annoying and complicated. We were looking specifically at spatial augmented reality and found positive feedback where, with some limitations, obviously. So do you think that perhaps putting all of AR into one category is a bit too broad, or did you even consider just because it is admittedly tablet-based is the most fun?
I'm afraid your voice was very broken.
Yeah.
I don't know why, Lorenzo. Just please repeat just the last part of your question, otherwise we won't have time to ask questions to Ricardo.
Sorry.
It's not getting better, Lorenzo. But if I got it right, you assume that whether that the people just perceive it as annoying to use the tablet, and this is what we also found out. So it was kind of the VR was very exciting, images were kind of boring, and also the 3D printed products, they were kind of cool. They were new, and the AR was kind of okay. I don't know how to hold the tablet, and then they had to, I don't know, adjust it the right way, and then some people just didn't really, they weren't that sophisticated in using the tool, and that was kind of hard for them. I guess so. They had kind of problems with that.
Okay, so
what you also mentioned.
I kindly ask Tina to be super short.
Super short, okay.
The last question by Charlie. So can you clarify the term technology acceptance?
Yes. So we measured technology acceptance in two ways. We had the system and the participants, so the person itself, and we measured them with 6 different aspects for the acceptance profile of the user. It's like the technology affinity, or the true innovativeness, visual information processing, and stuff like this. And the system was also measured with different items in 4 aspects. And there we had different things like, let me think about this, what we really had there. Also the ease of use, the control, the benefit, advantages through the technology, and the perceived pleasure and experience. Yeah. But of course, there would be many more that could have been analyzed.
Yeah. Okay, thanks a lot, Tina. And obviously, for any further curiosity, I think that you can catch up later on, also during the gathering event that we will have at the end of the day. So I would like to move to Ricardo Real's presentation. Can you please, Ricardo, open up your mic and show yourself? Great. The first question comes from Lorenzo. I will read it as we are running out of time. Did you manage to automate the process whereby the remanufacturing occurs between version 1 and version 2 of the prototype? You mentioned Boolean operators, but can you generate machine G code directly from this? Two questions in one, in the end. Open up your mic, please.
Yeah, hello, sorry. I thought I'd got
Problem?
away with not answering any questions, but to answer Lorenzo in short, kind of, we're almost there. We can align the two models, and automating it then isn't too much of a problem. So where we're at is a stage where you can align them, segment the differences, and you could automate the process of generating the repair G code, but only if you have the two digital files. Something we're also looking at is if you do not have the digital files for both. So if you have, for example, a physical prototype that you don't have the digital for, but you want to capture it, which kind of leads on to Chris's question, where he asks about metrology, and that is something we're looking at. So you can scan a prototype, capture the digital, and then be able to remanufacture future versions based on physical prototypes.
So thanks a lot, Ricardo. In the end, you answered more than two questions at once, not just Lorenzo's, but also some part of Chris' question.
Thank you.
So I think that the first part of Chris' question is still relevant for the discussion. So how might manufacturing defects in the version 1 of the prototype affect their remanufacturability?
I think Chris would have to clarify what he means by defects.
So something that I think that
it's
something that it didn't work properly in the first round of manufacturing. So you manufacture something maybe through 3D printing, and not everything comes to the, yes, exactly. So it's what you just wrote. 3D printed part might have worked.
Yeah, okay. So this, I think, would come down to some sort of user experience in the end. If a lot of the part is significantly different or damaged, then maybe it would be best to just print a new one. But if it's only a small defect, it could be that you could quite simply remanufacture the changes and well, save time.
Okay. Further questions? Because if there are no further questions from the audience, maybe I will take the chance to ask one question to Ricardo. So what are the challenges that you think you will need to face when you move from simulation to the real world?
I think it comes down to the times not always being the same, and a lot of uncertainty in the case of the user's experience. So they might have less experience with the digital alignment of models, for example, and that could be somewhere where it takes much longer than expected. So it could be that these things take a while. Another challenge is, of course, comparing the times of actually doing it physically to the simulation. A lot of it's based on hypothetical numbers that are kind of more or less along the right lines, but there's still some uncertainty in the values. Some of the work we've been doing with students, they've actually been doing this and have managed to remanufacture a couple of different prototypes, and we have a good range of examples of parts that have been machined and remanufactured into something completely different. If you look at the kind of time and cost, you'll see that they kind of are similar to the results of this study, but there is still some difference.
So we still have 1 minute, so I will try to make it short. I have a curiosity. In the final words of your paper, you open up to opportunities related to circular economy. What do you think the industry should do to implement remanufacturing practices? What are the barriers to face? And what would be the cost on the CapEx side?
Well, one of the issues is the tools aren't really there yet. So the idea is there, but something that brings everything together, the pre-processing and the execution and so on, isn't as available to the user. So part of it is creating these tools that people can get on board with and start playing around with. And the other part is demonstrating that the benefits to industry, for example, the cost savings that can be achieved. If you have very expensive materials, then it would obviously benefit manufacturers to be able to remanufacture.
Okay. So I don't have much more to say. I see that there are no further questions appearing in the chat. We are getting close to the conclusion of this session. Let me thank all the authors for being so responsive, for all the questions coming from the audience, and also for interacting with each other so efficiently. Actually, I didn't have to do much, as you noticed. Let me also take the chance to congratulate again with Lorenzo and Tina for their papers, and obviously please extend my congratulations to all the other co-authors. And that's it for this session. I think that there is a small break before the keynote speaker. The keynote speech will take place in approximately 15 minutes, if I'm not wrong. And I asked Philip to correct me if I said
yes,
something.
that's true.
Okay, correct. So see you in the podium space, and then with the next sections taking place at the end of the day. See you all. Thanks you all for attending. Bye-bye.